Vicky, thank you very, very much. It's a pleasure to have so many of you here. It really is. Thank you so much for providing me with this opportunity to talk about some of the things we've been doing back home in the UK. I say UK on the slide, but much of the focus is going to be about what's happened in England, because the four nations that make up the United Kingdom each have their own peculiar education system. My work is really focused on the English curriculum. I'm supposed to do a little bit of bio by way of introduction. 18 years as a school teacher working across 4 different schools, much of that time as a primary ICT coordinator, as we used to call the subject. 3 years as a primary, call it elementary if you will, head teacher, administrator, hence prematurely grey hair as a result of that. 8 years, the last 8 years I've been working at the University of Roehampton, training the next generation of our staff. So much fun. I love my job. It's great fun. It really is. Roehampton very kindly let me out to do other things. So I serve on the board of computing at school and the British Computer Society's Academy of Computing, as well as being a member of the Raspberry Pi Foundation, and now as international on the CSTA board. I was part of the panel that drafted the English program of study, the curriculum. We have the vaguely the your standards, and have been involved with quite a number of the implementation projects since then, and it works. Really. Okay, so what we're going to do over the next hour or so is walk you through some of the stuff that we have available back home, which may be of interest to you. Okay, I know you've got a different education system, your own particular challenges, but it's still the same computer science. It's still Scratch. It's still Python. It's still. So I'll talk a little about what our curriculum is, share with you some of the resources that have been for students, some of the resources that are available for teachers, very, very quickly touch on some of the assessment materials that are available, as well as then talking about how we've approached the challenge of professional development. All of the slides are online, so I don't have to pose for photographs in front of them. bit.ly/CSTA 2017. That URL will be on the final slide at the end of the deck as well, so don't worry if you miss it now. Okay, so on then with the start of this curriculum. What we have is a new curriculum. We had the old subject, ICT as was. You might think of it of the skills in using particular office applications. There was a bit more to it than that. We did have some programming on there, but not very much, and tended to be on more in the breach than the observance. Our Secretary of State for Education back in 2013 decided it was time to make a change and said we were going to disapply the old ICT curriculum, leave it up to schools to decide what they did in that space, but then commissioned an expert panel put together by our Royal Academy of Engineering and the British Computer Society to draft a new curriculum, a new set of standards for computing education. We've replaced the old ICT curriculum with a new computing curriculum with help from Google, Facebook, and some of Britain's most brilliant computer scientists. I'm fairly certain he did not have me in mind at the time we were talking about that. The Facebook thing, anybody from Facebook in the room? Okay. The Facebook thing. They came to one meeting, and I don't recall saying anything. They probably just liked what we'd done, which is okay. Okay. We have an entitlement model of curriculum. Okay, so I know it's a different education. The Secretary of State says every child from the age of 5 to 16 should be taught these things. Okay, now you know what's going to happen when it gets down to school level. Yes, the Secretary of State for Education may say so, but the actual implementation of that is a whole other matter. But we start from the premise that this is something every child is entitled to. And I think that is the most exciting thing that we've done. We have set up an agenda of this is #CS for all. And that's really very, very important. It's not just for the boys. It's not just those from nice middle-class homes in the leafy suburbs. It's not just for those who've got parents who happen to work in the tech industry. It's not even just for those who are interested in the subject. This is an entitlement for everybody. Why do we teach everybody music or poetry in school? Not because we need more professional musicians or more professional poets. Perhaps we do need more professional musicians and professional poets, but because this is part of a rounded liberal education. And the same applies, we believe, to computer science. Everybody should learn about this whilst they're at school. Yes, some will then go on and get jobs in the tech industry, which is great, force for social mobility, but this is so much part and parcel of all of our lives that we all should understand something about. We start with this ambitious sentence, a high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. And for many of us, we think this is the purpose of education, that a young person leaves school understanding the world in which they find themselves and being empowered to make do that. Computing education fits within our curriculum because it contributes to those end objectives, understanding the world, being empowered to change the world. And I think the two work hand in hand. The computational thinking is about understanding the world, a new way of looking at problems, a new way of looking at systems. And the creativity is about making something that wasn't there before, making a positive do that work. We have three elements to our computing curriculum. We characterize them or describe them as computer science, information technology, and digital literacy. But nobody is entirely clear about where the boundary is between computer science and information technology and where the boundary is between information technology and digital literacy. So I think it's easier to think about them as the foundations, the applications, and the implications of the domain. The foundation, the principles of computer science, the fundamental ideas that underpin how we look at problems, how we program computers to solve those problems for us, to automate. Applications still matter. Getting useful things done with a computer still part and parcel of what a child, young person, should be learning at school. Yes, being able to move the cat across from scratch is tremendously interesting, but in all honesty, being able to is probably going to be more useful for quite some time yet. The way we think about problems. But we also want them to learn some of the implications. Yes, for themselves as individuals, so that they're empowered to be safe in an online space. More than that, so they know how to act responsibly. And the best of it, to think through the implications of our reliance on the role of algorithms in society, for them as individuals. So it's not just science. Okay, so before we get on to national curriculum, our youngest children, children before the age of 5, we call this reception, we call this nursery school, there's a framework for what they should be taught. Don't worry, we're not teaching them to code in Python at that age, okay? But we are laying the foundations of computational thinking at that point. No mention here of computers, no mention here even of lovely digital programmable robot toys. This is all about how you tackle a problem, how you work creatively and collaboratively to solve problems. So before a child gets to the age of 5, they should have learned to have their own ideas. In fact, they probably have their own ideas, even if we don't teach them to have their own ideas. Thinking of ideas, finding ways to solve problems, finding new ways to do it. They should be able to make predictions, they should be able to test out their ideas. They should understand about grouping, about sequences, about cause and effect. They should also be able to plan and make decisions about how to approach a task. They should be able to check whether their things are going well and change the strategy. If you're all computer science, you can see how that will later feed into the stuff which they scratch, the stuff which they Python, and the stuff which they will do when at university when they get Google. I've spoken with Google engineering directors in the room. That's pretty much what you're looking for in your new recruits. Yeah. Take them straight out of kindergarten. No, don't take them straight out of kindergarten, please. Okay, for 5 to 16, we have the national curriculum. Despite what I said earlier about this being an entitlement model, the legislation says it only applies to children, young people who are in local authority supported, maintained schools. Independent schools and schools that are directly funded by central government have the option to move away from this if they so want. So there is an entitlement, but it's not an entitlement for absolutely everyone. I'll just give you a moment to copy this. No. All of this is online. Of course it's all online. And if you go to the slide deck, link through to the original documents. Point worth making is the content here fits onto 2 pages of what we call A4, you may wish to call letter paper, which is exactly the same amount of space as the CSTA standards take up. Okay, they're not the same, but there's a lot of common ground here, and that shouldn't come as a surprise to any of us. They're young people, they're children, they're learning computer science. How many different ways are there to do that? Okay, so things worth pointing out. Key stage 1, our 5 to 7-year-olds, we don't expect them to be programming on screen. It's fine to be able to program a little floor turtle to trundle around the mat. We introduce them to the idea of an algorithm as a sequence of steps, and then have them code that algorithm as a program on a digital device. As well, I think importantly, is making a prediction about what code or what an algorithm will do. Up in 7 to 11-year-old territory, key stage 2 as we call it, yes, they're programming on screen by that point. We have a number of requirements for their programming: sequence, selection, repetition, variables, input, and output. Write me a drill and practice program in Scratch independently by the age of 11, and there's a big tick in that box. It's a standard-based approach to assessment. If they can get to there by the age of 11, then they're meeting at least the programming requirements. There is more to it. Key stage 3, we introduce at least one more program. This is 11 to 14-year-olds, and for them, there's this idea of at least two languages, at least one of which is text. Most are using Python as their go-to language. So we have that transition from the block to text at some point between the age of 11 to 14. 14 to 16 is kind of just fitted in at the end there. Broadly speaking, is keep calm and carry on coding. Is continue the development of what's gone before, but there's not a huge amount of new content coming in 14. That is an elective subject. Everybody has to learn at least some more, but if you want to pursue a qualification in it, that's left to the individual student. So we have a set of requirements for our qualifications at 16 plus GCSE computer science, very similar in scope, but not exactly content, to AP CS principles. And then at A level, which is the 18 plus school leaving qualification, high school graduation in US terms, there's again another elective course there. Very small number of students pursue that. Last year, about only 6,000 elective. We hope we have this pipeline coming, much more, many more takes. Really interesting in there. Okay, so we've produced guidance for that because it's a very slim document, and the guidance again is online. What are the resources that are available for students themselves? Much of the work we've done at Computing at School has been focused on teachers, but there are things which are aimed directly at students themselves, one of which I'm holding in my report now, the BBC Microbit. So our national broadcaster, the BBC, gave one of these to every 11-year-old country last year. That's notionally 1 million or so of them. And what a fabulous idea in terms of a resource for children themselves. Okay, challenges over implementation. Actually, putting sets into schools and getting teachers to do interesting projects with children and these microbits might well have been more effective. You've just got to admire the confidence, the vision for just giving one to every 11-year-old. What could you make with one of these? And I think that's fabulous. So the code on screen here is a block-based interface using the make code, I think it is, from Microsoft. So we have a little bit of programming here, runs inside an event-driven loop. So when we shape the thing, we set the item to a random number between 0 and 5. 0, 0, 0 number. We then add 1 to that to get something in territory. We show the number on screen, we wait for half a second, we clear the screen. Now you could all read the code. Very, very simple. Started. What's that going to simulate? Real world system. Am I modeling with this? Of course. Okay, so one of these, just roll a dice. And the extent you can take this on from there is phenomenal. It really is. And so we've got now, in certainly the Microsoft PXT toolkit, this make code interface, the ability for one microbit to talk to another microbit. BBC were very worried about that when they thought out children would start cyberbullying one another by their two-button interface on a microbit. Okay, what's the rudest message you can type using Morse code? But you can do all sorts of lovely agent-based modeling of having microbits sort of spread a message across the classroom. There's lovely stuff. And we've got the quick start guide for teachers because we realized even within the implementation that the best way to get children involved in this was to give teachers some way of introducing it to children. And so a few simple project ideas in there. Okay, I've not been for code. BBC, again, our national broadcaster, have produced lots of lovely resources as part of their sort of revision support material. Certainly applies at 16 plus when children are taking those school leaving qualifications, 16 plus qualifications. There's also some great content in there lower down the school as well. So even from 5 to 7-year-olds, there's some lovely interactive resources and some great videos online. I can't show you the videos because the license only allows it in the UK. But you can read the content still. So here's one example of this. We're very familiar with bubble sort. We learn about merge sort and quick sort. And what about bucket sort? Bucket sort is a really efficient algorithm. So pop them into the right bucket and then sort each bucket. And then you have the ordered list. Actually, in some circumstances, more efficient than something like quick sort. And that's from the BBC. We've got a team at Nottingham University making videos for students who are learning computing. Anybody looking at the Computer File YouTube channel? What do you think about it, sir? It's great, isn't it? Do you have a favourite video? Okay, I mean, they are brilliant. They really are. And, subscribe to it, point your students towards it. This is more sort of top end of high school, I would suggest, but concrete problems in AI safety, how onion routing works. There's some really high quality content in there aimed at students. And then, of course, the Raspberry Pi. And Raspberry Pi has been out for, I think, just over 5 years now. Tiny wee bare circuit board computer. Put your hand up, please, if you've got a Raspberry Pi of your own. Keep your hand up if you're doing something cool with it. Okay, that's good. What are you doing, sir?
We turned over ports.
Yeah.
A pie on the back of it.
So cool. What age are these? Okay, that's great. One more example? Yeah. Is that using the Oracle Raspberry Pi workstation? Fabulous, really does. So what Cambridge University are advocating, probably our strongest computer science department at university level, is not that students do that 18+ the A-level in science. The students get themselves a Raspberry Pi and tinker, learn how to have a go at a project of their own choice, using the Raspberry Pi as a starting point for that. And I see Raspberry Pi fitting in very, very well. This much lower down the school. You can use these at the top end of elementary school. You can use these very, very comfortably in middle school. Raspberry Pi, I would hesitate before bringing in that low during the educational journey there, but certainly top end of high school. Students working independently on these things. There are some great resources from Raspberry Pi. So Raspberry Pi runs, I can never say this, Raspbian, it's a Linux version there. You've got Minecraft Pi Edition, which allows you to use Python as a way of scripting what happens in a Minecraft world. You have a free copy of Mathematica. Now, there are people in the room who get pretty excited about Mathematica. You and me both, okay? But it's a very expensive tool, even with an educational. It's a Raspberry Pi and run Mathematica. And Sonic Pi, which, anybody seen Sonic Pi? Okay, Sonic Pi is worth the demo, even if the speakers on the machine don't work very well. Okay, so here we go. This is a version of Ruby written by a guy working at the computer lab in Cambridge as a way of getting students, young people, to play around with music as a medium for their coding. So they write their code and that produces some music out. I can't compose well, but I can type numbers in. Okay, you can say you could do that in Scratch, and of course you can do it in Scratch, but it's lovely being able to do that. Link that with coding. It's another means to make their coding, their computer programming projects creative ones. So we also have from Raspberry Pi Foundation, a whole collection of educational resources. This is education in the broadest sense. Yes, there are some things aimed at teachers, but there are some really nice sort of community maker projects in there, and some resources which are entirely accessible to top-end high school students. The latest wheeze from Raspberry Pi Foundation is wiring 8 Raspberry Pis together to make your own supercomputing cluster. Supercomputing cluster for about, what's that going to be? $280 or so. That's not bad, is it? So let me just show you what that looks like. So here we go. This is public key cryptography. It's a whole walkthrough here, so we work our way through the introduction. At some point, we need to know about finding factors to numbers here. So if you're given a number 12 and asked to find out its factors, what strategies would you take? Could you talk to the person sat next to you about how you would go about finding all of the factors for a number like 12? Please, chat. Yes, sorry, okay. It's a pause. Talk. Anybody got a good method? Okay. I need a volunteer who's got an efficient algorithm for solving this problem. Okay, so tell us how you're going to find all the prime factors. That's true. Okay. This sounds like a really sophisticated solution. Anybody got a simple solution? Prime factor trees, you would just find two numbers which multiply to 9. If one of those isn't prime, then split it down. Then how are you going to work back up the tree to find all the factors? All the possibilities? Yeah, okay, I like it. I like it. Do you have a simple solution? Okay, anybody? Yes, in the background. Yeah. So 20 by 0 would be a really bad idea. Don't do that. Do that mistakes. We don't do that. Divide by 1, we get 1 goes into 12. Okay, 2 goes into 12. And 1 times 1 by 12. That's great. I like that. That's a simple way. I can just do a for next loop and get to an answer there. So the worksheet takes us through, and then we get to the programming challenge. After you program, alter your program so that it takes any number the user types in and outputs all of its factors. Here's one I prepared earlier. So using the function to find the factors of a number. So define the factors of a number, start with an empty list, start with the number 1, until we get up to the square root of the number. If it goes in, then add that number and add the number of times it goes in to the list. Keep going until we hit the number. There's a little bit of finesse at the end if you take a square root, if you take a square number, and then return the sorted list. Do you want to see it working? All right, here we go. So what are the factors of 28? I get 1, 2, 4, 7, 14, and 28. What are the factors of 8,192? Anybody like to tell me some factors of 8,192? Okay. There we go. Okay. And 8,191, we get that. Okay, so it's just playing with the code. It's a lovely way in to starting to understand how public-private cryptography works. Anybody from the NSA in the room? Okay, getting away with it. Okay. And so, and then, of course, we're going to head into big territory of working with big numbers. And does your algorithm work? We start, putting in, 100-digit long numbers. Will my algorithm work more efficiently when we put in long numbers? Control Tab. There's the presentation slides. Good. So you've got that from the Raspberry Pi Foundation. Sorry, I missed a slide there. Sneaking in. Okay, we'll come back to it. Oh, I know where it is. Okay. Also, top end of high school, top end of our secondary school, we've got this wiki book. So for that 18-plus school leaving college, there's a team of teachers working together to make a crowdsourced text which prepares students. Such a fabulous project. Yes, there are published textbooks. Yes, there are endorsed by the exam board. But having a textbook there which covers the syllabus for free is a big deal when it comes to social equity and access to science. And of course, look at the bold sentence there. If there's something wrong with that, don't complain about it, correct it. And that's exactly what we ought to be doing. What about for teachers? Loads of resources for teachers as well. We have this sort of small government thing going on back home. So, design principles for government service. Let's strike a chord or something. Okay. Government should only do what only government can do. So we had a Secretary of State who said, yeah, okay, make computer science education happen. Here's the curriculum, everybody has it. And then stepped way back, any of the detail of implementation. So there are no state-created resources. There's no, okay, they have got examples by the government, but they've not done any of the detailed work about development, or resources, or really assessment, or even inspecting and evaluating curriculum. All of that has been left to the sector, the people, to do for themselves. And so we as an organisation, Computing at School, which is a sister organisation of CSTA back home, have stepped into that gap. Publishers too have stepped into that gap. And so we have from British Education Suppliers Association, Publishers Association, a list of requirements, expectations, guidelines about what a good textbook for computer science, computing education should look like. I've been involved in producing this one in Claire here, switched on computing. We also have the middle school scheme. We had a whole pile of those on the table at the back of the room, but the people in the previous session have helped themselves to those. Sorry about that. So what we're doing in Switched On Computing, which is elementary scheme, we cover both the information technology and the computer science bits and embed that digital literacy, the implications throughout things. We take real-world context. So, for instance, Year 4, which is, I think, the equivalent of 3rd grade, we are software developers. Children work together to develop a simple educational game. It's the usual sort of drill and practice. What's 3 times 7? What's 4? Maths. We're toy designers, building or at least prototyping an interactive toy, producing digital music. Could do it with Sonic Pi, don't have to do it with Sonic Pi, editing and writing HTML, working together as a wiki. And yes, presenting the weather, not so much dealing with the sensors to get that weather data in there, but once you've got a prediction about what the weather will do, how would you make a prediction, how would you present that to an audience? We're selling this overseas as well. So this is going down very well in Spain. I think we've had Qatar expressing some interest. The We Are Metrologists has to be adapted for international audience. If you're working in Qatar, what will the weather be like tomorrow? Hot and sunny? It becomes less of a challenge, it really does. Okay. So this is one of the, this is Year 3, 2nd grade problems. We've got this, you know, the car runs around the track here. I'm hoping that I can just Control-Tab into the live code there. So you've got this, here's some Scratch code. Is there anyone in the room who's never seen Scratch before? Okay, no! Okay, it's lovely to have you here. So, we're going to put the car on the track. We're going to set it going. You've probably done something similar. Yellow bumper touches the green thing, turns to the right. Blue bumper touches the left, and keep trundling around. Anybody like to use logical reasoning to predict what the car will do? Roll around the track. Okay, let's have a go at that. I'm going to just take the speed down here whilst we're practicing. So speed equals 3, variable notice. Trundle, trundle, trundle. Oh, I could watch it all day. I really could. Okay, now what did we have earlier? We had variable speed as 10. So let's try that and see what happens. Oh no! Bug or feature? Okay, so feature, this is part of your citizenship education. You drive too quickly, you will lose control of your car. So how do you get around that? Well, just, you know, the faster you go, the more you have to sort of steer. So let's try changing that. Whoa! Okay, I don't want to go on a road trip with that person, I really don't. Okay. We start with that, fixing the bugs, okay? How does that go wrong? Can you explain why? Yeah. If the jump forward tab takes both bumpers off track, carries on in that direction. So fixing it properly without just finessing those numbers, really, we end up with like some blocks to get a proper fix. I'm sorry, I said that. I'm very happy. Sorry. What else have we got? But you get into other interesting territories. You know, we've got Google and we've got Uber and we've got their own cars. Somewhere in the logic flow, one of these self-driving cars, there's got to be code similar to this. I assume not written from scratch. If the car goes off to the left, turn to the right. If the car goes off to the right, turn to the left. What other rules do you give the car? You know, if a child runs out in front of you, then slam on the brakes. In fact, if any person runs out, slam on the brakes would be one of them. But what other rules? Sooner or later, we get into moral choice. Yeah? If you have the choice of running into 4 people or running into 3 people, what should the car choose in this? And who's liable? We start with a very, very simple debugging exercise, and then go into really interesting territory around that digital literacy implications side of computing. Okay, so Control tab. There's the presentation. Okay. Barefoot computing barefoot computing was just such a lovely project to work on. Why is it called barefoot? It's an interesting. So, the notion back in Maoist China, Mao had this idea of how do you improve medical treatment across a country of 1 billion people, the whole of China. What you cannot do is afford to train a doctor in every. What you can do is one person and give them enough medical treatment, 90% of the problems present. And so without where the name came from, we spun up barefoot computing. We don't need a graduate computer scientist in every elementary school. It would be lovely, but graduate computer scientists find other things to do than become elementary schools. So what you need is one teacher who knows enough computer science to be able to pass that knowledge to their colleagues, to be able to teach their classes the content, the standards of the curriculum. And so Barefoot was based around that idea, and we produced the concept guides to cover the computer science. But we also produced the exemplar activities, how to put it into practice. And one of my favorites is the sharing sweets algorithm, because, very young children need to learn how to share things. What's your algorithm? You've got a pile of sweets. How do you share that between 4 people? You talk to your friends. Now, please. Okay. Who's got a good algorithm for sharing sweets? One volunteer, please. Anybody? Oh, anyone? Yes, go on. Yes. Oh, that's lovely. I like it. Yeah. Okay, tell me how you divide the sweets into half. So you've got a stack of sweets, yeah? How would you yeah. Count them? Talk me through this. I love this method because we can generalize that. Yeah? Your method will work with thirds, sharing 30 people. Yeah? So we've got a general solution. Okay, we guarantee. Okay, so we may have an edge case. There are going to be some certain quite disparity. In half. So really nice example and something which children and, crucially, elementary school teachers can work with, yeah? We're teaching this idea of algorithm as a sequence of steps. We're teaching this notion of generalization, that method would work for any number of sweets. We're teaching the notion of, well, I think, those are the 2 key things there, of abstraction. We didn't actually have to have the sweeties on the table to be able to think through how we would do that. So we're covering a lot of this computational thinking territory, and you could see how that algorithm would be extended into larger numbers. Code Club is now part of the Raspberry Pi Foundation and runs some brilliant after-school coding clubs. So this isn't part of the curriculum, but we know there are lots and lots of teachers who are using these great Code Club projects as a way of teaching introductory programming from scratch, some lovely text-based coding in HTML and CSS without having to worry about any algorithm. as well as that step on into Python whilst children are still at what we call primary school. I think I have an example of one of these. Okay, so yeah, so this is one of the Code Club projects. We have the rock, paper, scissors game. We create a list. We ask the player which one they're going to choose. The computer picks one at random. If they match, we declare it as a draw. If a player picks rock and the computer picks scissors, then the player wins. We can have a go at the code here. Rock, paper, scissors. I'm going to go with rock. And it's a draw, okay? Any problem with this code? We're missing a number of the cases, and of course, in the Code Club, you can give the skeleton of the code, or as Sheena suggested, start from the blank screen, as Code Club generally do, and then add in that, build it up to that point, and then add in the other cases there. I'm not going to do that in front of you now, because I will make mistakes if I do. Okay. Computing at school has this repository, and I know CSTA has a repository as well, but we've set the bar very, very low. So any teacher who's a member of it, come and share your lessons. Come and share the PowerPoint slides that you use. Come and share the homework sheet that you set with the other teachers who are members of Computing at School and now with the world outside. So we have now 4,156 resources on the CAS repository wiki. It's a wiki. All of these are editable things. They're all tagged against the English curriculum as well as the other curricula. But you can figure out what works in relation to CSTA standards if that's what you would like to do with that. So I would recommend that to you as, sorry, the wrong way, as something which teachers themselves have put together. We've also worked on some of the advocacy challenges. We have this problem of how do you persuade school leaders, how do you persuade administrators to take computer science education seriously. The Secretary of State for Education saying it should be taught is not always enough. And so we produced the leadership toolkit there, matters in the UK, but more important, every child the essential thinking skills they need to succeed. And we think the arguments are persuasive. We would say that, wouldn't we? Assessment is a challenge, okay? And, how do we know that children have learned these concepts? You can look at their programming, but looking through lots and lots of programming projects and trying to work out if the child understands an idea like abstraction or understands the notion of algorithm is really, really hard. Asking questions may well be the way to go. So one of the things I've been working on this year is crowdsourcing this national item bank of multiple choice questions to assess computing. We call it Project Quantum for no good reason. It's not to do with this is the smallest amount of learning that you can ever detect, nor is it to do with some statement about if you know where the child is, you can't tell where they're heading. It's just it's a cool name. Okay? It's free in the sense of free beer. You don't have to pay for any of these. Okay, it's free speech. We set the bar low for the content. As long as there are no rude pictures, no rude words on the right hand, you can submit a question. It's also free for you to use however you want. We'd like you to use it on our platform, but you can download the stuff. You can put it into a Moodle site, you can put it onto a PowerPoint slide. You don't have to use our platform for these questions. It's also free in the sense of free kittens, in that the work isn't done for you, okay? That we're not sort of curating a whole scheme of work, a whole sort of curriculum that you can just deliver, just sit children in front of computers doing one question after another and they've learned. Science doesn't work like that. It doesn't work here. We're focusing on formative assessment. Do not use high-stakes testing. It's online, but you can print it off if you want. Automatically marked. Doesn't work. Aiming for high quality here, but we're letting the data speak. So there's this stuff you can do in assessment theory called item response theory, rationalysis, which says once you know how good the learner is across a range of questions and how good a range of learners are at doing one question, start mapping the two together and getting some measure for the difficulty of a question and for the ability of the learner. And we're aiming to get to that point very soon. And it's about supporting. Yes, kind of teaching to the test, but if the test is a good one, if you choose the content of the test, that may not be necessarily a bad thing. Yes, measuring progress, big deal for us back home. They couldn't do it, I taught it, they could do it. That's the sort of data which school inspectors and educational leaders are interested in. And most interesting for me, figuring out what it is that large numbers of our students don't understand about computing. A equals 10, B equals 20, A equals B, code on the screen there. It's fine when it's in Scratch. Suddenly when it moves into Python, lots of students get that wrong. I think mainly because of each variable. Here's a question for you. You can do it on your own, you can talk to your friend. It's better if you talk to your friend. Who here actually knows any Python programming? Okay, so you've got the advantage here over the others. Okay. Given the following program written in Python, what would it display if the user typed in 1? That's meant to be a 1. It's a bad choice of font. Choice equals input, choose 1 or 2. If choice is 1, that, else print that. You've got 4 choices to choose from. Okay, so talk to your friend, agree on 1. I'm going to ask you to shout that out in a few minutes' time, seconds' time. Okay, so what we're going to do now, I'm going to count down from 3. When I get to 0, I want you to call out one letter from the range A, B, C, D, only, okay? Here we go, all right? Yes is not a helpful answer. 3, 2, 1, 0. I'm getting a lot of different answers. Somebody definitely said A, I think. Who said A? Tell us why it's A. Yes. Okay, otherwise.
Okay, 3.
Right. Okay, and what about D? Who said D? Are you persuaded by his argument? Ah, right, okay. Okay, this is down to your choice of version of Python. It's a very good answer there. Are you interested to see how students did? Okay, here we go. This is what our survey said. So 28% of them got it right, okay? 28% is not brilliant, because you have to bear in mind that a room full of monkeys will get 25%. 46% of them picked D, okay? And, you know, I've got anecdotal evidence from teachers who've used this notion of Python as the type of which they don't remember. They, you know, if you give this as code and it doesn't work, many students will be able to think, they remember that. Okay, sneaky. And there are issues, I'll admit. I hadn't spotted the subtlety about Python 1 versus Python 2. That's a very good, Python 2. So for our vague equivalent to CS principles, it isn't the lovely CS principles create. It is what we call the NEA, the non-exam assessment. And what you have is a period of 2 weeks, 20 timetabled hours. The student is given a brief at the start of it. They're not allowed internet access during the period they're working on the assessment. They're not allowed to take anything in, they're not allowed to bring anything back out. And they've got to write a program that is a brief. And one brief we have in the specimen materials is 1,000 back home, so can you guess what the mystery number is? And it's a really nice programming task aimed at that sort of 16 plus, but doing it without any of that sort of the things that we rely on when it comes to writing computer code, I think makes it significantly more challenging than otherwise. Okay, we've done that bit. Okay, that's the brief. So we start then with, yes, of course, import random. Sheena, that's always a good thing to type into any Python program. Generally, we have, because of the brief, this thing about validating whether the guess is a valid guess, which actually makes the game a lot harder. The code which compares the guess and the code and the actual secret code itself, which is quite subtle to get that right, of scanning through the list, checking whether it's in the right place or checking whether it's in the wrong place, and then the implementation of the main game loop of enter your code, and then iterating until they get the final version of this. When I had a go at it this morning in preparation, I managed to be very, very lucky in the choice of numbers, so I'm not going to do the live demo of that now. Okay, whoops. Okay. Present. Okay, so we talked about that. A-level questions, there's an exam paper when it comes to the 18-plus school leaving qualification. And for that, we're getting into territory of functional programming, so an introduction to Haskell as part of that. And you can use these questions. You know, if you're interested in having a look at what questions we're using and whether you can bring them into your courses, you're more than welcome to do that, which gives me 15 minutes to talk about the most important thing, which is professional development. So computing at schools. Membership organisation, very similar in many ways to CSTA, about 27,000 members at the moment. We've grown like Topsy in that sort of phase between the implementation of the curriculum and publication. 3 clear phases. Very, very gradual growth at first, 30 of us around the table. Semi-exponential growth phase, doubling every 7 months or so. Take over the world at that phase. And it's now sort of leveled off and sort of linear growth. Now as more teachers are learning to joining our community. It's open to anybody in the world. You do not have to give a UK postcode or national insurance number to become a member. I'll give you the joining code shortly. Very vibrant quite vibrant forums. Some people, become quite sort of, sniffy computer scientists. That's not the way I would do this. But we're trying to encourage, teachers to ask any question on there. No question too simple, small, or stupid. So file management 3 and 4 from Brett Reynolds there. And so general questions, elementary, secondary. Also a forum there to promote diversity and a number of much more specialist forums, discussions in there as well. Professional development really does matter. So a lot of this we can do through a community of practice model of connecting teachers with other teachers. But learning computer science, the quote from South Korean official, quality of an education cannot exceed the quality of its teachers. Very similar to the CS for All statement, which was something along the lines of, if we want great computer science in every school, we've got to have a great computer science teacher in every school. Yeah? The teacher quality really does matter when it comes to this. We have this Mishra and Kohler TPAC model, the knowledge you need in order to be an effective, essentially 3 domains in our life. The content knowledge, the thing you are teaching, pedagogical knowledge, the how to teach, as well as the technological knowledge of how to make the kit work, which is something which can get overlooked. And they, Mishra and Kohler, of course, look at the interactions between those domains. We simplify this for how we're thinking about this back home and say, to be an outstanding teacher of computing, outstanding computing depends on pedagogy, tech skills that they're using the kit, and CS subject. In the early phases of implementing this new curriculum standards, we've said pedagogy we're going to take for granted. We're going to say teachers know how to teach. This may not be entirely accurate, but let's do one thing at a time. Most teachers know how to use tech, okay? That we don't have to do, this is where you plug the computer into the whiteboard, this is how you get to a website. We're saying that those things, if we need to address that later, we will come back. But what really does matter is science subject. Uniquely in our national, this is the body of learning. Teaching history, teaching math, you learn these things when you were at school. You didn't learn how to teach them, but you learn the content. Science. Most of our teachers never learned how. Never learned. We've got to address that first. We want them to be effective teachers, confident teachers, creative teachers of computer science. So we drew up the list of subject requirements. If you're going to become a specialist in primary, elementary computing or in secondary computing, there's a list of stuff that we felt you should know. And this becomes the entry requirements to initial teacher training for computer science, which is pedagogy. It also becomes the blueprint for professional development. Much of the professional development in schools has organised, it's focused on covering these bases. And again, I'll give you a moment to copy down the detail. Okay. Barefoot computing feeds directly into that. Okay, so yes, we have the exemplar activities in Barefoot, but the focus of Barefoot is making sure teachers learn just enough computer science to be able to teach elementary computer science. We focus very much on computational thinking. We do mention unplugged approaches like our sweetie sharing thing, but computational thinking lies at the heart of our golden thread running throughout it. And we kind of inspired by the Brennan and Resnick approach to assessing computational thinking. We identify there's a set of concepts there on which computational depends. Logical reasoning, algorithms, decomposition, patterns, abstraction, evaluation, very, very similar to the list which Google were promoting 4 or 5 years ago now. But we also say there are a number of approaches which the effective teacher should be encouraging. Science, tinkering, playing, experimenting, seeing what happens if you bend it, if you break it, making a view of learners learn best through making. Absolutely. We're trying to do, certainly in elementary education, fixing things when they go wrong quite a lot with us. Persevering, keeping going when it gets hard. Absolutely. Yes, it's really important to learn about us. It is actually really much more important that they learn to become hard, and that they effectively together, that they learn to collaborate, although that is discouraged during the exams. Okay. We produced a set of concept guides to all of these bits of computer science for elementary school, and they're all online. I'll give you the URL later. We've moved on from barefoot into lower secondary now. We said that in secondary the challenge is harder, or it's different. That typically secondary computer, ICT as was, computing as is taught by somebody who has some background. It may not be a degree in computer science, might be business, might be working using IT out in industry, but they have some knowledge of it. They don't, though, have the hinterland, the background knowledge which a degree in computer science would provide. So my colleagues who've worked on the Tenderfoot scheme have said, let's try and address that. Not so much learning how to program in Python or other lovely languages, but the stuff that you won't get just through doing a programming course. Plenty of programming courses around, but you won't learn about finite state machines just through doing a learn how to code in Python. You won't learn about how the internet works just through learning to code for yourself. So we've covered that. Quick start computing, the idea for quick start was the cascade model. So we have these CAS master teachers. You have to forgive the gender-specific language there. We have CAS hub leaders, vaguely the equivalent of chapter leaders in our terms, who are providing professional development for the teachers in the schools that they're connected. What we wanted to do for them was to produce the CPD pack, the professional development pack of resources they could use without too much preparation with the teachers who they're working with. So the cascade model, if they go and be trained in the content of Quick Start, then they have the teachers in the schools they're working with. And this has been really very, very successful. I feel particularly proud of this. So the primary one is covers the whole of the the English elementary school, primary school curriculum. Quick Start Secondary was much more about pedagogy, about planning, about assessment. But we found that there was a real need to address subject knowledge. So I produced the 3rd volume in the set last January. That's gone like hotcakes as well this morning, I'm afraid. We say, start with the BBOTs in elementary school, move on to Scratch, move on to Snap as a sort of nice transition from Scratch programming, and then cover Python. Typically in the Key Stage 3 version of Quick Start, we're presenting the same program in both Scratch or Snap, depending, and in Python. So teachers can see side by side what it looks like in both languages, and we don't say when the transition has to happen. If you want to work in a block-based language up into middle school, that's fine. At some point, they should make that transition into Python code. And we have some examples of this. So this is the usual guess a number type problem here. So this is not so much writing the code as a way of teaching the principles of binary search. So demonstrating binary search, let's run the code and see. Okay, I'm thinking of a number between 0 and 127. What's our guess? 64. Who would have predicted that as a first choice? Okay, that's too high. 32. Too high still. 16. Still too high. At this point, you kind of worry, have I written the code right? Is it actually working? Okay, too high. Oh no! 4. Please work. Okay, 2. Oh, thank goodness. Okay, so at which point I think we will all guess 3 and get it. And of course, this illustrates beautifully that binary search is not always the most efficient algorithm. We've got, is it 1, is it 2, Is it 3? We've got there. It's just 3 steps on this code. Thank you very much. Okay. Right, where are we? So what does this do? I'm not going to be able to show you all of these lovely quick start activities, but we can get at decomposition through programming. What we're trying to do with a lot of the quick start material is link together the computational thinking and the programming, which is something Brennan and Resnick do very well. I feel that, yes, learning to make a jam sandwich, sorry, American translation, peanut butter and jelly sandwich is great. But this is more cookery than it is computer science, in all honesty. Yes, knowing that there's a sequence of steps is important to any understanding of one understanding. But being able to automate that process, being able to automate the guess the number game or the bulls and cows game is really important to computational thinking. Computational thinking without the computation is just, well, thinking, really. And so, yes, decomposition, but link it to programming. So you've been waving your finger around. Have you figured out what the if you've done that without access to the computer, only mine in front of you, being able to think these things through, being able to reason about code, very, very important in what we're trying to do. And so we show the program in both Scratch there and Python underneath. You can see the similarities between them. It doesn't matter, it's the same idea. At some point, yes, we want you to know where to put the colon and we want you to remember what the syntax is for a for loop in Python, but it's the same idea behind the code. Oh, and debugging exercises. I've not got time, but that's great fun. There's, figure out. Actually, we have got. No, we've not got time, but let's do it anyhow. Okay. There's the Turtle graphics stuff. Debugging challenge. Okay. Can you tell me any bugs that you can see in the code here? I may or may not be able to make that bigger. There we go. Yes, just call out, please. Go on. Yeah? Oh, if you want, yeah, I think that's fine because X is a time sign, but that's now a star. Sorry, it's a small font from the back of the room. Any other changes? Yeah. Say again? I do indeed. Well spotted. Well done does indeed need quotes. Oh, very good. I'm going to leave. Yeah, okay. Do they? A and B are probably okay. Okay. Oh, right. Yes. Okay. With you now. So stra A plus stra B. Yeah, like that. Yep. Yes, it should. Oh, that's very clever. Right. Smart. Anybody got one more? Shall we run the code and see? Okay. Just for a moment, recognize how brilliant you all are because that was debugging without running the code. Yeah? That's a step up from running the code and fixing the error messages. Being able to read the code and see what's going to go wrong matters. Okay, so let's have a go at this. Oh dear, error message. And, being able to cope with the Python error message. In Scratch programming, you never get error message. Occasionally, you will see a big red circle come up, but you have to be really bad at Scratch programming to get that, or really creative. Okay, so it gives us some hints. It says there's a problem here for I in range 10, and it says it's a name error. So this was me being really sneaky, I'm afraid. That should be a 1, not an L. Okay. Sorry. Font choice. Okay, so we've got it working. No error messages. What is 12 times 12? It is gross. Oh. I'm fairly certain. Let me do the math in my head. Yeah, 144. What's going wrong? Yeah, so that's where I thought you were going with the string conversion. We need answer is casting that as an integer of that input, and then we should be okay, Vicky? Oh, yeah, I'm going to have to restart the kernel to make it working. There's one other error here. Anybody figure out what the other error is? Go on. Yeah, absolutely, which is apparently bad educational practice. It's nice to vary the question in the test. So putting A and B inside the loop is the thing which we need to do. But just following the error messages doesn't get you the string casting. Oh, okay, so CAS TV, which is a YouTube channel with like 40 plus videos of, believe it or not, me interviewing eminent computer scientists and computer science educators with a view of how to take this advice and make it practical in the classroom. We have Simon Peyton-Jones CAS's chair in the first of the series, in which he reveals CAS's official policy on the P versus NP question. So watch that. Does CSTA have a policy? I don't know. Okay, we've got Hello World magazine, free magazine, online at the moment in the States, hoping to go to a print edition in the States before very much longer. Computer science educators, digital making educators. We very much welcome contributions from anybody here for the next edition or the edition after that for Hello World. We have a certificate in computer science teaching, which I think is pretty cool. Yes, there's accredited CPD as part of that, at least 20 hours, at least 10 of which should be face-to-face. There's also a programming project. You can't get the BCS certificate unless you can do your own programming project, ideally with a practical classroom focus, and then a classroom investigation. So some sort of mini research project based in the classroom. Some really good questions coming up from that. Very much welcome you all to join CAS. There's an authentication process. We don't let children into the CAS community site. You've got to prove that you're a grown-up, okay? Because we don't want children being in the same forum as their teachers. In order for you to prove that, at the second page where it says authentication code, CSTA-MB-2017 will get you through the sort of prove that you're a grown-up question. No children in the room. Good. Okay? And very much finally, here's all of the URLs, here's all of the addresses. Okay. Right. Yeah. The only one you need is the top one, because this is the last slide in the deck, and so. Okay. Good. I'm sorry we overran, Vicky. Thank you.